AutoCheckIN aims to reduce the amount of time spent in the waiting room by automating the check-in process. Through face recognition, the system will log the patient in automatically and calculate their body height. In 2010, people in the United States spent 1.1 billion hours seeking health care for themselves or for a loved one. A research done by the Harvard School of Medicine estimated this time to equal $52 billion. Opportunity cost is defined as the amount spent doing an activity, which is calculated by measuring an individual's income based on the same time. The same study estimated the opportunity cost during a clinic visit to be $43, while the average out-of-pocket cost for the same clinic visit would be $32. The amount of time spent at the doctor's office can be divided into three categories. Travel time to and from the office, which is estimated at 37 minutes. Time spent with non-physician staff, which is estimated at 64 minutes. And finally, the time spent with the doctor, which is estimated at 20 minutes. In order to effectively reduce the amount of time spent with office staff, our system has been divided into two subsystems: facial recognition and height measurement.
For face recognition, we first detect the faces using the hard cascade classifiers provided by OpenCV to generate 30 samples of the same face and write them to disk. Then, we load the training data, which we formatted so each user corresponds to a certain ID, and return a list of IDs and face samples. After that, we just use the same cascade classifiers to detect and extract faces from the video to recognize the ID of the user and output the corresponding name to the screen if it is found in our dataset. So first we capture an image that we load into our system to pre-process it, find the contours that are then sorted from left to right. We then find the pixel per metric ratio using the width of the reference object, and finally display the dimensions of that object and an estimate of the height of the person on the image.
So let's look at our evaluation criteria, our proof that we have something working. First off, our subject demographics. We had 11 subjects, 8 were male, 3 were female. They were between the ages of 20 and 66. This was a mix of SMU students and staff. And a testing occurred throughout the day on June 16, 2017. For our facial recognition, you'll notice 2 rows highlighted. These were subjects who were being detected as not only themselves, but as other people. And what we noticed, the thing in common was that these people wore glasses and the people before them wore glasses. So our system could not completely differentiate between the two. So out of a total of 10 people that agreed to go through our test, 8 of them were positively identified, meaning they were identified as themselves and only themselves. And while we'd like to say that this is an 80% accuracy rate, we realize that the sample size is just way too small. And even if we were to accept the data as our accuracy rate, we'd have to say that it's still not acceptable for real use just yet, because other models are able to detect faces are much more accurate than 80%. We'll go on to our height estimation. So you'll notice that we have our measured heights, and then we have our 3 different measurement heights. These highlighted rows are ones that were the most far off from their real heights. So this is our first series, and we see a large difference in values for subjects 5, 8, and 10. We had problems with subject 5 due to the light color of their shirt and their fair complexion. Subject 5 would get caught off by our bounding box and get an underestimated height. This similar situation happened with subject 8. Now subject 10 had issues, but this was more related to when we did our evaluation. The time was around 5:20 p.m. and the sun was on its way down. Our room was not as bright and it affected our system. If we go to series 2, see our mean squared error is 19.74, which is less than series 1, which is at 31.9. So better, but definitely not good, especially if we want to make this real system. You'll see subjects 5 and 8 still had issues as mentioned above. Subject 10 had a much better measurement. Subject 10 adjusted their position from our reference object, which gave us a better contrast between them. And finally, Series 3, which again does not have a great mean squared error. And you'll see that subjects 5, 8, and 10 are still showing poor performance. You also see that subject 9 had poor performance this round as well, and it was due to their head positioning, which made our model not box all of their body. So we see that subjects 5, 8, and 10 are pretty bad. What happens if we just take them out and take the mean squared error of that? We get this. We get something with a mean squared error of 1.7, which is way better than anything else we had. But it's still not close to 0, which is what we would want for a mean squared error, but it's much closer. So while it is much lower than before, we really can't conclude that this would be good enough for a clinic to use. So some concluding remarks. Our systems are not really good enough to be used in real-world applications. Lighting greatly affected our height estimation system. In our facial recognition accuracy, while it's 80%, really it's just on a too small of a data set to really conclude anything.